Well, welcome to the uh, Structural Modeling January additional um, event here. We're going to just have a kind of open discussion on a few topics. The international workshop is going on simultaneously with this, so other people are engaged with that, so I'm not sure what type of additional participation we'll get. So we'll just kind of see how things go today. Kind of unstructured approach. So, see, Kevin is on. He's had some questions about strict order, partial order, and so forth, how that relates, I guess, to um, the global and local type of relationships. And so that's something that's really quite important, foundational. And what we have is up on the screen is the version from Wolfram of what a strict order is, right? And I know that Kevin has he's just on his phone, so I don't know if he can actually read this, so I'll read it and kind of explain what I think the major um, portions are. And that's a strict order is a relation, right, over a set that has three logical properties: irreflexive, asymmetric, and transitive. So we really like that. That's uh, very focused. It has three well understood logical properties. They work together. But where we have a problem with this is that there's as it goes down through this particular definition, it says every partial order induces a strict order, and then every strict order is total if A is less than B, or B is less than A, or A equals B. So in the mathematical definition, where we run into problems here is in the equality, and also the lack of distinction between a strict order and a partial order, because it says every partial order induces a strict order. So for A to equal B, logical properties have to be reflexive, symmetric, and transitive. So now we have uncertainty between what is a strict order, what set of logical properties we're working with, and exactly what it means. So that's fundamentally what we're driving at. Does that make sense, Kevin? So in this particular case, when we look at it from the logical properties standpoint, then we have went and looked at the literature to actually how these aspects were applied. And when we looked at the three fundamental functions of the ISM software, we had the priority structuring, we had the clustering, and then we had the general modeling function. And what we found in looking through, like the handbook of interactive management, also looking through the science of generic design and other areas, is that in many cases, what people would do is they would start with a clustering activity where they would cluster everything together using the equals, basically equals or in the same category as. They have an event and they would go through and they would make everything, they would take all of the issues or whatever they were focused on, they would take those and put them into groups and categories. And then later, after they'd done that, then they would do the operations on the category. So it was almost like a two-step operation where the ordering they were doing is they're performing ordering when the strict order sense on a set of objects that had already been grouped into categories. So they were making a strict order of the categories, not necessarily a strict order of all the objects that they were working with in that case. So that's the fundamental crux of the problem in the uncertainty and where where there's issues. Hello, Peter.
Hi, I'm here.
Okay.
I'll just go on mute now.
Okay. Well, we were just going over the fundamental issue of the uncertainty associated with partial order or strict order. And just to kind of recap, it basically says strict order we like because it has three very distinctive logical properties. But then where we run into a problem is the definition from Wolfram is that a strict order is total if one of the elements equals if A equals B, or if element 1 equals element 2, or element n. And so that creates a problem because for equality, it is reflexive, symmetric, and transitive. And so we have a conflict in the logical properties. And also it says that every strict order induces a partial order. And again, the same thing, it makes that uncertain as to what are the logical properties you're dealing with, and actually what do they mean. So we went through and looked at the literature, and we found that mostly in application, what people would do is they would do their clustering or their categorization first using the clustering function, and then they would order the classes that they had clustered the objects in, so that there was really a strict ordering, or there was a ordering of the categories, not necessarily an ordering of the elements. And due to the way this is defined mathematically, there's the uncertainty. So we want to be able to get rid of that uncertainty by naming an order, some type of order that doesn't allow the partial order. And so that's fundamentally the issue there with the uncertainty that introduces the complexity part. Hopefully that will shed some light on the subject.
Welcome, Janet. Also, Kevin is on his smartphone rather than his computer. His computer went away, so he's working with a very different interface, and I don't know how easy it'll be for him to slip in and out.
Mm-hmm. Yeah, I just grabbed lunch and made it back to my room, and so I missed your intro there.
Well, yeah. So Kevin had a couple questions. One of them was about partial order, and I thought that this basic definition from Wolfram kind of highlights all the components, because essentially when we're looking at our logical relationships, this gives a very good explanation of logical relationships for strict order. But then it says every partial order induces a strict order, and every strict order induces a partial order, right? So a partial order is going to need the equality, which is reflexive and symmetric. So there's uncertainty there. So we're trying to eliminate that uncertainty because that uncertainty introduces complexity.
Yeah, I find they're right up there confusing for, I would like to see more along the lines of what you had, though I didn't quite follow your graph. Strict as opposed to non-strict, and partial as opposed to total. But it seems here that they're mixing those two together.
Yeah, okay, so there is a lot of that in different sources, right? So you would like to look at the graph that we had. Let's see, let me pull that up. See if I can find that real quick. Here we go. Here. Now I need to find that one. And then I need to actually be able to share that. So stop sharing that, and we'll go over here, see if we can find it in the window. Okay, here it is. Wow. Right, so this is the one.
Is that the one you were thinking of, Janet?
Yes, that's it. And I wasn't sure about the included in. Is that the same as or different from the induces that Wolfram is using there? Or is it that if this holds, then that will also hold?
Yeah, so that's there's a lot. So there's a range of impact that could happen by that, and I believe what we're trying to convey here, the most basic thing, is that there's a decision that has to be made. Right over here, it says plus a selection rule. Right here, so we have a selection rule that says, oh, you have to make a decision. There's some if then else. There's some type of uncertainty here. And so you have to get some information, some empirical data. You have to do something and make a selection. And so whether, I'm not quite sure what they mean by induces, but obviously you can't have both equal and less than at the same time. It has to be one or the other, right? For a specific set of objects, object one and object two. So that's what we're trying to say.
So is this your graph or is this from someone?
This graph we modified from John Soa's work, and they were talking in their ontology and their artificial intelligence. They were talking about math theories, right?
Right. What was the website that came from? I remember that, but I couldn't find it.
Okay, that was Soa's website, I believe, or one of the lists. I could take a note to find that and distribute it.
Yeah, it was taken from some German site, but I couldn't remember.
Oh, I remember now. Yeah, so that was the right. That was the German website where right. So I can find out and distribute that website.
Okay, that would help.
But that's just a number of. So they were talking about the number of axioms, right? How many? Yeah. So what are the axioms? So we're not really looking at the axioms here so much as just talking about matching our real world experience and our real world vision, right, with these logical properties.
Okay, so is a selection rule added at each level to get you to the next level, or is it only at the fourth?
Yeah, no, the selection rule is only at the anti-symmetric level. only at level 4, right? So at the first level, level 1, you just have one logical property, just whatever it is, right? And those are the names. And then if you combine these two logical properties, let's say to combine reflexive and transitive, then that gets a new name. It's called a preorder, right? Or if we combine transitive and symmetric, we get partial equivalence. So those are just a name for, those are different names for basically the same fundamental objects. Just now we have 2, you just have 2 of these things.
I see. Okay, so the first level, the logical properties are the determining factors, and then the others are more names for the ways that the logical properties are grouped.
Yeah, you can look at level 1 as like bricks,
right?
Colored Lego bricks, and then the next one up is, this is the name for 2 Lego bricks put together. The third one up is, we have 3 Lego bricks here.
Right. I guess it was so I understand 1 and 2. I'm not sure why is 3 a different order, a different level rather than just more enumeration within 2 of cases of combination.
Okay, so equivalence you have to have, it has to be reflexive, right? It has to be transitive, and it has to be symmetric, right?
So equivalence, right? So equivalence comes from symmetric, reflexive, and transitive, right? So it's just, so usually I would think of that as that you would have those 3 properties all going into equivalence. But here you have a mediating case before you get to equivalence. I guess that would be another way of drawing it, would be having equivalence on level 2 instead of on level 3, but having the 3 reflexive, symmetric, and transitive feeding into equivalence.
Right. So this was just, so I believe the original graphic was talking about the number of axioms that was in, and so that from the top to the bottom, there was, I think, the least number of axioms was at the top, the smallest number, and the most is at the bottom, if I believe correctly. So all they did here said, okay, well, I'll just put the names of the things that we call, the basic logical properties, the basic bricks, just one, right? So, and then we combine those 2 and 3 and before. Go ahead.
Yeah, so you have 2 properties in level 2. So it's only pairs of properties, and the last property. What happens to the last property? That's another question. Because
you mean up there in 4 or?
No, I guess in 2. If you're looking at symmetry, reflexivity, and transitivity as being the characterizing bricks, then this is an aside, but I'm not sure what is the non-case? It's like you have the black and white, the anti and the pro, that it's either yes or no, and then the non is ambiguous to me. Does that mean that it holds in some of the cases but doesn't hold in other of the cases, or pairwise within your set of objects?
Okay, so I'm going to need to understand a little bit more. We can talk about, let's say, are we talking about level 1 or level 2 or level 3?
It's the level 2, the non cases, non-symmetric, like it's.
Right. I got it. Okay, so the non-transitive, the non-reflexive, and the non-symmetric, right?
Right.
Okay. So in these cases,
so it seems like maybe it holds for some of the pairs, but doesn't hold for other pairs. If it didn't hold for any of the pairs, then one could say the whole relation was non-whatever, because all of your cases would show that it didn't hold. Or if it held for all of them, then you would say, yes, the property holds. If it holds for some and doesn't hold for others, it just seems like there are a couple of ways one could get into that situation, but I assume that's what is called non-X, non-symmetric, non-reflexive, is that some of the pairs it holds and some it doesn't.
Yeah, okay. I think I'm beginning to understand what you're saying. And so there's a couple of different issues here. One is the organizing of the math theories. And then the other idea is, what are we applying these math theories to, okay? And so if we're applying these math theories to a group of real objects, and we are relating these real objects together using the set of math theories, then when we're relating these real objects together, then we could have object A is related to object B in an asymmetric way. Right. Then we could have object A is related to object C in a symmetric way.
Right.
And so if we took those real objects as a group, we would assign them a non-symmetric type of name tag.
Right. It definitely seems that, yeah, so the non-cases come from something that is driven by, by observation, not by the mathematical side, but it's driven by the real side.
Well, it's a real configuration.
Right.
It's a real configuration. Right.
It raises, in practice, I would think that if the property held in some cases, not in others, that could either mean that you hadn't defined your relation well enough, because it just seems odd to me to ascribe the non-X label to the relation when it's the empirical data which has given rise to the fact that I guess I would think maybe you'd want to say you have a relation, sub 1 appears to be symmetric and relation sub 2 is asymmetric. But when you call it non, you say, the overall relation is non-symmetric.
Right.
And I guess also in some cases some of the pairs are not comparable, so that you can't like in a hierarchy when you have across a level, you can't determine a relationship one way or the other. That seems like indeterminate. It just seems like the third value here, you need a 3-valued logic, and the third value can be either undetermined, or it can be both, or does that make sense?
Yeah, I think it does, Janet. I've struggled with this a little bit myself, and I felt that putting this chart together helped to create a environment with which we could talk about these issues in a little more detail. But I think that fundamentally, the idea is that when you're talking about these logical relationships here, where some of these logical relationships need to apply to a group of 2 or more objects, right? So non-symmetric, right? If I just had one object, or or one relationship that I was talking about, right? It couldn't be both symmetric and asymmetric, right? It couldn't be that. It would have to be one or the other. But if I had a group of these objects that we are now talking about, the relationship that basically organizes this group of objects. So we're really talking about organizing relationships here. And so we could have an asymmetric organizing relationship. And so all of the objects had an asymmetric relationship. Or we could have a relationship that said, oh, we have all of these objects and they all have a symmetric relationship. Or we could have a relationship that says, oh, it's non-symmetric, meaning some of these objects have a asymmetric relationship and some of them are symmetric. And you will see that specific graphical representation of that relationship throughout the ISM literature, and especially throughout Warfield's literature. They didn't give it a name, but they drew it. You know, they drew it in the structured graphics and they encoded it into the matrices, but they didn't give it a name.
Yes, I think this diagram is very helpful to bring these questions out. I'm still troubled by the non-case. I'm not sure.
It needed some name tag, and I agree with you. It's not that. It's not. Let's say it's a start. It's a start.
Right. Yeah, it reminds me of the Italian flag approach to evaluation, where they have red, green, and white.
Yeah.
Bad, good, and but the white can be mediocre, or it can be undetermined, or irrelevant, or various other but various other aspects of that third case.
Yes, I agree. So the multi-valued logic here, and when we're talking about collections of objects that we're mapping a relationship over a set of objects. And so one of the real fundamental things here that applies to systems is that if you define a system as a relationship mapped over a set of objects, then these are basically system level relationships. They happen between individual objects, but you have to have a set of objects for the system, right? And so they have to have more than one, more than two. You have to have.
Mm-hmm. So if you had, does that relation mapped over a set of objects construct hold if you had mammal, dog, cat, Fido, Rough, Fluffy, and Pussy or whatever? You had a hierarchy that a nice typical hierarchy like that. Is that a relationship mapped over a set of objects? Or I also, you said briefly something about categories versus instances.
Mm-hmm.
So what about my basic case there of mammals and dogs and cats? Is that a relation over a set of objects?
Well, you could. It's well, okay. So the name tags, right? The name tags you can assign to a set of objects, right? You can do that. I can say I have a set of these names. Okay. So that's and so now these names are all related somehow, these concepts, these names, right? They're all related somehow. How are they related, right? And what are the attributes of that relationship? So if we have a hierarchy, right? If we have a hierarchy, what are the at the logical attributes of that relationship. Asymmetric, irreflexive, transitive, I'm not sure.
Right.
One way.
So in your
one way is transitive.
Right, that's right. In each of those, so I guess you have threads there: mammal, dog, Fido; mammal, dog, rough.
Yeah.
Those are, as you just said, asymmetric, irreflexive. Don't know about transitive. They're orders, right? They're strict orders.
Yeah.
Yeah. But and I yeah. Now that you can't draw comparisons across. You say, what's the relationship between Fido and Fluffy? And there is no direct relationship between Fido and Fluffy. So the absence of a relationship, does that mean non? No, that doesn't mean. What does it mean?
Yeah, so that's excellent. That's okay. So we have two cases here, right? Okay, so you have two cases. You have a case where you cannot have a relationship, and then you have a case where, oh, there is always a relationship, right? And so we're trying to engage that specific set of concepts and attributes using the terms global and local, right?
Right, right.
So global, there is always a relationship, and it's usually always single-threaded. And then local, right, is saying, oh, okay, local could be a hierarchy. A hierarchy has many threads in it, right, as you pointed out, right? And so that the relationship across those may not exist. That's what allows the multiple threads to go through there. A key aspect of modeling and dealing with this type of approach, what we really want to do is we want to think about how the logic of this propagating relationship applies to our real world situation, because systems scientists, systems engineers, we're in the business of properly aligning the mathematics with the real world situation. And so there's a lot. So Warfield defined what he called strictly local. But he didn't really define the global relationship and its characteristics. He called them propagating relationships. He said they were propagating, and then non-propagating were strictly local. But and he assigned the propagating relationships only to the class of logic. And he said there was, other real world interactions that were propagating, right? But, and you can model them using the logical pieces, which is what we're doing. That's what we're trying to do. We're trying to use the logic to properly select and match real world situations so that we can model it correctly. And so, you talk about real world like interaction and process and impact and so forth. So if you take the concept of a global relationship, right? And you talk about a billiard table, right? So you got billiard balls, and you shoot one and it impacts the others and they all hit each other and they all move, right? But each time they move, they lose some energy. They lose some force. There's friction, there's momentum loss, there's all that going on, right? So in that case, then what we have is that's not strictly local. It's not strictly, it's not a strictly local thing, because the energy transfers from the first ball to the second ball to the third ball, but finally somewhere down the line, the energy, it just, dissipates, right? So there's some scope. Go.
That's very interesting. So So even though what is that? Is that a hybrid case? That seems.
Well, it's a boundary case because, like global, logical is infinite, right?
Right.
So there's no energy loss in logic. There's nothing to reduce or impact
right.
that connection as it goes out. It's just logical, right?
Right.
A is bigger than B, C is bigger than so on and so forth. So there's no dissipation of that connection. But in real world situations, we do. So we could do things like in the billiard table. You could say, well, I'm going to scope this to where I'm only going to have 3 balls, and I'm going to have, greater than X amount of foot-pounds force. So I'm going to assume that this acts in a global way within the boundaries of what I'm talking about, right? The behavior will be that way. So anyway, then we have strictly local. Then we have what we call local, which includes strictly local, but something else, some kind of, scoping variable. We're working on that. And then global.
Right. So another thing I noticed, so all that's very interesting, and I'd like to learn more as you tease that out about the local, global, and boundary cases. In your diagram here, another question is why is there strict total order distinct from strict order, since only that one feeds into it?
That is a very good question. And again, knowing the provenance of this specific chart coming from the mathematicians and the artificial intelligence ontology guys, right? And from the strict logic side, trying to answer that question is what has driven me to look at a lot of different sources.
Right.
And it's confusing. I think it depends upon the school of thought and who you are.
Right.
It's not clear to me, but it was in the chart, so there it is.
Okay, that's the end of my questions at the moment, I think.
Okay. Excellent. Well, Peter's listening, so let's see. So we covered global, local, strictly local, and we covered partial orders in this chart a little bit. Let's see. Is there any other? Let's take a look at some of the other parts here. See if we have those. So, Peter, did you have any questions, or are you still just listening?
Yeah, I'm happy to be listening at the moment. That's fine. This is probably more in Janet's bailiwick, as they say in English, in terms of the hierarchy of math series.
Okay.
Yeah.
We want to make it very clear, and we want to make it so it applies specifically to types of.
I guess maybe I might ask that you've got like 4 levels there. Is there any other number of levels, or why 4, or is that how it just fell out?
Oh boy. So this is let's how to start with this. Okay, so there's many different kinds of logic. There's all kinds. We took this as fundamental to just talking about the relationships of a structure of a system. There's no modal time here. There's all kinds of many different kinds of logic that we do not even approach. So this is very basic. There could be.
Well, I mean, what would come above partial order, for example? I mean, order, full order, whole order?
Oh no. Let's see. So let's say we did like modal logic. We brought in time or something like that, right? We're not. You can talk about using these types of logical approaches. You can talk about ordering time, right? But it's difficult to express different states, different contexts, different conditions that happen at different times in different states. So this is fairly straightforward and does not really.
Yeah, but it is a snapshot then in time, isn't it? I think maybe that's perhaps your point or my point or understanding of the point is that it's an ordering as of now and how to capture any evolution or development or something.
Yeah, doesn't address the higher order logics at all, I guess maybe.
Yeah, so even if you could give, not today obviously, but even if there was some way of actually just showing this in a map of how this related in higher order logics might be a really helpful thing.
I've been thinking about that. I need to look at a couple other aspects, but I might try a little later on when I get into I'll think about that. I'll make a note on that.
Well, one thing would be to take your comprehensive approach in looking at the three key properties and then saying that each one of them can have three values. And then, as you did, what are all the possible combinations? Some of these don't make any sense or never occur or aren't of any interest. I don't know. I'd like to see a systematic treatment. I guess we talked about this back when you showed that German map, because it didn't seem like they had taken a really systematic approach in generating all the cases. They more looked at the theories that are actually used, it seemed.
Yeah, so that's really a good point. And I think and some of the things that I'm struggling with is trying to make this a little more matched back to engineering, and how do we take these things and map them and to help us work with designing and creating and engineering things. So one of the things that I thought might be interesting to do is to just take an idea of the AMEI connections and then think about, okay, what happens with, let's say, where this is a connected electric system, and we have electron flow. And so the concept of connectivity here means that the electrons can flow. They're all connected, so we have a circuit flow. Well, that's fairly fundamental approach. So we could talk about that, but then we could say, well, what happens if we have physical connections, right? And we allow a conductor and insulator in this. Then we have places where we have some electron flow, and then or places where there is no electron flow, but they're all still physically connected, right? So the ideas of, looking at the connection logic of the AMEI, that's kind of one picture. But then as we start looking at those and saying, well, what are these cases? Then we need to kind of look at some approach that says, well, some physical instantiation of those. And like you're talking about, these will happen, these will never happen. But this represents that type of situation. And so those are things that are very important. But it all takes time. Okay, so that's that one. I think that the other one here, of course, had some good exchange with Len, and he liked this chart. So this one here presents us the types of truth, and I really think this is kind of, from the logic point of view, we're really working with the formal truth, but we must be able to make a connection between the factual truth, which is like the real world, the value truth. That's what we're doing in the sim. Start matching those together. And that's really an important part that we haven't really looked at much because we've been working on the formal piece right now. So it's that part is, I think, very important. And then there was one other one. Let's see, the last one I sent out on general systems theory. I'd like to get your impressions on this one because it's not really clear to me. What the specific all right. We're trying to, in this particular case, place general systems theory between mathematics and a specialized discipline. Did people recognize that as a definition of general systems theory? You took this in bolding, and because you put it between mathematics and specialized disciplines, and mathematics is also one of the formal languages that Warfield talked about in the process of trying to make that connection, make it a little more concrete.
Is this your diagram that you've created?
Yes. Yeah, this was about technical point. Yeah, so we wanted to, so we're working to start establishing and talking about the system pattern. So the semantics, like what we've been talking about here, the semantics of the logic comes from formal rules. And the semantics of the GST comes from a derived system pattern. And then, of course, the specialized disciplines are determined from domain context. And one was saying that they've got about 50 patterns. It would be interesting to start seeing if there's a way to start mapping those to the AMEI characteristics.
Where would the 50 patterns come from?
Let's see, it's Len's.
From Len, yeah.
Oh, from Len. Oh, okay,
yeah.
Sure. Oh, sure. So you would take Len's and start mapping it. Yeah, that'd be cool.
Yeah, it would be to see if there's a connection between them, right? And so you just go through and just take a cut. So I thought that would be a fairly interesting way to start looking at these patterns. Okay, what kind of logical rules, right, map to the pattern? Is there some type of connection between those? And then, of course, the derived system patterns, they're interpreted differently in each different domain, but you should be able to at least identify and categorize a specific pattern that's essentially unchangeable. So that's kind of where we are there. How's the IW going?
Well, it just started really, so we're getting a sense of what's happening. I think the one thing that struck me this morning was sort of the challenge to think about systems engineering in the context of global issues, and in particular mentioning sustainable development goals. And there's about a good 25, 30 people in the system science working group session here. So that's off to a reasonably good start in that respect.
Excellent.
The hotel is a bit disrupted. They have damage from Hurricane Irma, but so far no real problems, I don't think.
All right. You're able to stay dry, eat and drink coffee and talk.
That's right. Yes. And if systems engineers can't improvise and be flexible, I don't know who, we're in big trouble.
That's right. I mean, I was wondering too, and as you're talking now about sort of the IW and so on, Len's work is more about processes. I'm not sure that he called them patterns. I'll have to ask him about his distinction between processes and pattern. I wonder if there are some systems engineering patterns that you could do the same sort of thing, Joe, and obviously you'd know more about that than perhaps even I would on.
Well, I think there's a number. There's a number of engineering patterns. They're going to map fairly directly. There's a number that map very directly, actually, to the logical pieces, processes, and.
But I mean, it might, for this particular audience of systems engineers, that if given your background in systems engineering, and also, the fact that there's such a lot of interest in the systems engineering world, and in fact, your name was brought up this morning in the work you're doing by Len, actually, and sort of recommending it. I wonder if that wouldn't be a task to do, and whether it would, provide an immediate sort of connection to the Nkosi world.
Well, so we've done. Let's just take, for example, the strict order, right? So everything that we're going to do within a strict order of time on a project, right, where all that kind of fits. But what this work is doing right now, mostly what it was designed for, was to evaluate the problem that you're going to use systems engineering to solve.
Right, I know. Yeah, well, yeah, I get it. I'm just sort of, okay.
So we can basically definitely talk about that interface, or we can talk about how far we want to bleed over into the sequential problem-solving process, right? But right now, the components and tools that we're developing to address the problem definition can definitely be used, probably reconfigured, right, to be used in other areas.
Right. Well, thank you. I've got to get back to the IW, so I'm going to sign off. Thank you.
Okay. Thank you very much, Peter.
Thank you.
Anything? Yep, you're welcome. Thanks for dropping by. Janet, anything else you'd like to say today?
No, that was very interesting. I'm glad you are taking this approach and got these charts together. It's good food for thought, but we should run it as well.
Okay. Well, take care and have fun.
You too. Bye-bye.
Good luck.